Okay, right. Thank you for the introduction, Till. As well, I'm Rasmus Zetter from Aalto University, working in Lauri Parkkonen's group on neuroimaging methods, specifically on MEG, and for me specifically on MEG using OPMs. So what I'm about to present to you is basically early this spring we had a need for a new coil, and then we got a bit excited. So that ended up in this software package that we're planning to release soon. So what is this bfieldtools? So it's a Python software package that will be released as open source during this fall, hopefully. And what it has, it was originally meant for coil design, but then why not open up the backend to all kinds of things? So we have gradient operator, Laplacian on a surface, and yeah, everything is on triangle surface meshes here, so that's the key. And we can not only do coil design in this framework, also compute thermal magnetic noise, as well as do some spherical harmonics analysis, which is more quality of life. So yeah, it's all about surface currents here on triangle meshes. So typically you might have surface current density. You express that using some basis functions. This might be Fourier basis on a 2D plane or an infinite planar on a cylinder or whatever. But if you go to a triangle mesh, it becomes a bit more general. You can have arbitrary surface shapes, whatever you want. So we approximate, when we discretize continuous surface into triangle mesh, we approximate the surface current density with this scalar constant, and then a set of basis functions which for each element in the mesh will have corresponding basis function for all the neighbors for that element. I'll just quickly show you the equations. You don't need to look at these too closely. So for example, inductance and resistance, these are matrices. So M and N correspond to the square matrices, and they correspond to the node indices. And what you see here is these V basis vectors, some surface integrals that in the implementation then become quadrature points and areas, and just coordinates, geometry mostly. And this C here is a coupling matrix, I call it, and it should look familiar. It's based on Biot-Savart. So when computing a magnetic field, we take this coupling matrix and dot product with the scalar constant of the current density. So I just like to point out that these aren't new equations. This framework has been used for MRI coil design for more than 15 years now. And yeah, I think the novel thing here is that we're sharing this openly and hopefully getting more people to use it instead of having it as kind of a secret sauce. Right, so moving on to coil design. So what we kind of want to do is typically have a maximally efficient surface current distribution on a surface, coil surface, that fulfills some kind of field specification. And your kind of cost function might be minimal B field energy in the coils, or minimum resistive power, or any kind of combination of these, or you might have some kind of smoothing weighting factor as well. And the nice thing is all of this is convex optimization. It's nicely behaving, and it's not too tricky at all. So in the case of minimum field power, you have here the equation for power energy in the inductors. You have the surface current density, scalar part of it, and then the inductance matrix, and we want to minimize that. We have some constraints, and if you remember the coupling matrix times this S equals B field, so with some shuffling around of dimensions and so on, we can put here the field specification and error tolerances that we want. And also any other inequality that is linearly dependent on this surface current density. And finally, we don't want any current on the edges of a mesh. It should obey proper laws of physics. So we just, in the same way, coupling matrix times the surface current density, we set those elements to 0. So this S, after running this quadratic optimization, this is what it might look like on a coil surface. So This is surface current, or the stream function S, rather, and this would create a field behind the projector in the Z direction, the vertical direction. So how do we go from this to actual coil windings? So, well, you do this. Just take the contours at a set number of points, and then, well, you might see where this is going, like this. And these are now closed loops. So there's, at this point, some manual work in connecting all of these in series in the right directions. But how you might do that depends a lot on the geometry of the coils and how you want to manufacture them and so on. So, yeah, but it's not a big deal. And of course, since you're actually just taking contours of a more or less a piecewise linear function, you can just choose however many windings you want and adjust your current to field conversion factor that way. And as long as you don't go too sparse, it doesn't affect the field profile significantly. Right, so for a user, what might this look like, the workflow? So you create some kind of mesh, the coil surface, where can I put my coils? You give a field specification, in this case, of these green dots here. We want a homogeneous field there in this direction. And on this red sphere surrounding the geometry, we don't want anything more than, let's say, 0.5% of the field in the homogeneous volume. And in this case, we set the minimum field energy criterion, run the quadratic programming solver, and create these loops. And it's a 1-minute process, more or less, running this. And just a small point, so we have minimum field energy, but still have this stray field criterion here. So that means that we might allow more total field, but we concentrate it between these two coil surfaces. Right, so just showing you some examples. We're in the Helmholtz Institute, so here I compare this kind of self-shielding coil creating field in this direction with a Helmholtz coil, and well, if you have stray field limitations, then this is something that you might want to do. Some other examples up on the left. This is a biplanar coil with like a 4x4 grid of homogeneous volumes, homogeneous target regions, and different field in each of these. I don't think that's a very practical application, but perhaps for some kind of array NMR where you want to get rid of a gradient. Just for fun, showing off, we can do any geometry on the surface of torus or a surface of an MEG helmet. So this is gradient coil creating a, well, not that great gradient, but gradient inside the helmet anyway. We can not only do coils on arbitrary surfaces, but we can also compute the thermal magnetic noise of thin surfaces. You divide the thermal currents into these modes, going from low spatial frequencies to high spatial frequencies. And then you normalize the contribution of each of these modes according to, based on the Laplacian matrix or Laplace Beltrami operator. And we can also model inductive effects at high frequencies. So here's an example of a thin film platinum, some kind of perhaps a heater or whatever. You can see here at the DC or white noise level, thermal noise. And finally, we have some spherical harmonics tools. You might want to look at, if you have measured a field or have a field model, how does the spherical harmonic component spectrum look like? And in some applications, you might want to map your surface currents directly to spherical harmonics basis. It's more efficient if you know that your field doesn't have that high frequencies and you want to know it at very many points. Perhaps, I've gotten some questions at QSM, when can I use this? So the plan at this moment is to polish up the code, write some proper documentation, create some more examples during the following weeks, and then write a really short companion paper and publish this, release the code at the same time as the preprint. Right, so this is kind of coming 2 months, I guess. Well, authors, so there's me and Jonas, who's also here. We're supervised by Lauri, who's also here. And we work on this OPM MEG mainly. Then there's also Antti Mäkinen, who's working on low field MRI with squids, as well as MEG. So I've been doing mostly in this project the coil design part and some of the back end, Jonas has been doing the thermal noise as well as spherical harmonics, and Antti has, when I made slow code, he makes better code. So, you know, he's been very essential to getting this working. And then, when we release this open source, perhaps we can get to collaborators. It would be very nice to have someone else also involved. And with that, I thank you. And if you're interested in MEG, please check Jonas's poster, which is right there.